Hey everyone, I hope you are all doing great. As we know, arrays and bit manipulations are the topics which can be a bit trickier in competitive programming. But don't worry, guys, to get a clear idea of these, we are back with our webinar on the array and bit manipulation. I'm Summer from the Coding Culture team. But before moving further, let me introduce to you about the coding culture. The coding culture is an initiative of 50 plus DAC chapter across India. This is a student-run open community program. The aim is to improve the coding environment and help students in their journey of competitive programming. It's a one-step solution to clear all your queries, good practice interaction, a full of competitions. So if you haven't joined the Discord community yet, do so quickly using the link given in the description. So today we are going to cover arrays, as arrays are one of the basic data structure out there and its thorough understanding is a must. So the speaker for the same will be Sumant. So yeah, Sumant is pursuing CHC from MIT Pune. He loves solving problems. He has participated in many code contests. And if you have any questions, put them down in the comment sections. We would love to take it towards the end. Okay. So, all right, the voice will be from Sumant. So, Sumant, the platform is all yours now. So, please begin and enrich us with the array world.
Yes, thank you so much for the introduction. Thank you so much. So, yes, as already introduced, the topic for today's uh, video, the live lecture or the webinar is arrays. So, without wasting much time, let's just see. I hope you can see my screen. Someone, did you add my screen? Okay, I guess I can. You can see my screen. Okay. So, starting with the topic, so arrays is basically a very vast topic and it's used for almost all questions in competitive programming. So, it's included somehow in almost all the questions. So, and it's one of the most basic data structures as well. So, first we'll look into the contents of today's webinar. So, the first we'll look into the basics of arrays, and then we'll be looking into two questions, easy questions that are one which tackles reducing time complexity of the problem, and other that reduces the space complexity of the problem. And then we'll be looking into two questions of medium difficulty, one which has greedy technique and the other which has DP technique. Okay, so let's start off with the basics of arrays. So what is an array? Array is basically a collection of items of the same data type stored at contiguous memory locations. So it's basically items or collection of items of the same data type. It's also randomly accessible. So if you want to access any element in the array at any position, you can access in with the time complexity of big O of 1. Previously, it had the disadvantage of fixed size because you had to declare the size of the array while initializing it. But C++ has come up with vectors and Python has lists which are dynamic arrays. So the size has not, it's not necessary to declare to initialize the size of the while initializing the array, declare the size there. Okay. So there are three types of indexing: zero based, one based, and n based. We'll not look into n based. So normally people use zero based or one based. In our whole lecture, we'll be looking into we'll be using zero based indexing. That means the first element has the index 0 and the last element has index n minus 1, where n is the size of array. Okay, so now we'll see what is a subarray and subset, because understanding the difference between these two is really important, because there'll be many questions on subarrays and subsets while you solve problems on arrays. So basically, for what is a subarray? Uh, for any given array, for example, the array given is A, B, C. A is a subarray of ABC, B is a subarray of ABC, C is a subarray of ABC, AB, BC, all these are subarrays of ABC. But AC is not a subarray of ABC because AC is not contiguous. So basically, Any part of the main array that is contiguous is a subarray of the main array. But what is a subset? Subset includes all combinations of the elements in the arrays. For example, AC is also a subset. AC is a subset, but AC is not a subarray. So I hope you guys understood the basic difference between a subset and a subarray. So for any given array of size n, the total number of subarrays are n into n plus 1 by 2. And total number of subsets will be 2 to the power n, because all possible combinations of the elements in the array. And the number of subarrays, as said, will be n into n plus 1 by 2. And this asymptotically we take also get the time complexity by this, that is n square. So to come up with all possible subarrays, we'll be needing n square. We'll see that later in the webinar. And so this last point is considering time complexity while solving the questions is very important, because often you'll come across this error TLE which says time limit exceeded. To avoid those, the key is to come up with a solution which is the most optimal solution. Okay, so we'll be looking into 4 questions, as I said. We'll start with the first question. The first question is separating positive and negative numbers. So let's see what is the question I have to say. So you are given an array n of size n, and it has both negative and positive integers. So you have to separate all the positive integers and get them to the left side of the array, and the negative integers you're supposed to get them to the right side of the array. Okay, so what is the naive solution? What is the most basic solution that you can come up with? So maintain two separate arrays. Maybe you can call them positive and negative, or vectors, to both store both positive and negative numbers separately. Traverse the main array. If it's a positive, store it in the positive array or vector. If it's a negative number, store it in the negative array or number. Else, so once you're done with this, you just merge those two arrays and you get the solution. So this naive solution takes a time complexity of big O of n and an extra space of big O of n again, because you need two different arrays which sum up to a size of n, that is the size of the parent array, the initial array. So the question is, can we optimize this logic to get the work done without using any extra space? So let's look at this. Let's think of something in that lines. So you are given an array which has elements 1, minus 2, 4, minus 5, 5 and 6. The idea is to get all the positive numbers to the left side and all the negative numbers to the right side of the array. So what I do is initialize the array, initialize two pointers, one at the beginning of the array, so I call it I, and other at the end of the array, and I call it j. So the value of j will be 5. Okay, here that is n minus 1, because I'm using n based index, 0 based indexing. Okay, so now I equals to 0. So what is the value of array at the 0th index? It's 1, and that's what we want. We want a positive number here. See, we won't do anything. We'll just increment I, and we'll increment I till a point it reaches a negative number. So when I reaches here, minus 2 is a negative number, and we don't want this here. We want negative number to be at the end of the array. Now we stop here and then we check for j. If j is a positive number, that's not that's not something we need. So we want to swap these values. So because array of j is positive and array of I is negative, we want to swap these. So the array then becomes 1, 6, 4, minus 5 and minus 2. Now the value of I is 1 because it was here, and value of j is still 5. Okay, so what next? Now area of I is positive. That's what we need. So we again increment I. It's again positive. At area of when I equals to 2, it's again positive. We again increment I. And I reaches 3. And when it's at minus 5, I stops. So when I equals to 3, it stops there. And j equals to 5. Now when j is 5, sorry, I missed out a 5 here. So j equals to 5, and since j is negative, that's what we need. We decrement j. We decrement j till we encounter a positive number. So it reaches 5, and because 5 is a positive number again, we swap minus I and j, the values of an array at position I and j. And then the array becomes 1, 6, 4, 5 minus 5 minus 2. And that's what we needed. We want to separate all the positive numbers and negative numbers, and we have done it in a single pass or a single traversal without using any extra space. So, and what is the terminating condition? The terminating condition is we have to stop when I is greater than j. So basically when value of I crosses the value of j, we don't have to bother anymore, because the whole, we got the desired result. So we'll just look at the algorithm for this. Yeah. So I equals to 0 and j equals to n minus 1, considering the zero based indexing. If area of I is greater than 0, I plus plus, and we have to do this till area of I is negative. And we have to decrement j till area of j is positive, and when that's there, we have to swap them. And then the whole time complexity is big O of n and space complexity of big O of 1. Okay. So yes, this is the code for it. While true, while vector of I is greater than 0 and I is less than j. This condition here becomes really important. Otherwise, it becomes an infinite loop, because the outer loop is while true. So we need a breaking point, and I greater than j is the breaking point. Okay, so when I is greater than j, it does not swap, but it goes into else and breaks. So this is the breaking point. This is the whole code. I hope you guys have understood the solution. And if you understood it, I would recommend that you try segregating all the positive and negative numbers such that they are present alternatively. So like the challenge is, given an array that consists of positive integers, positive and negative numbers, the first number should be positive, and then the second index should have a negative number, and the third index should again have a positive number, and so on. And the excess elements, it may be positive or negative, they should be present at the right end of the array. Okay, so in the previous question, we have reduced the space complexity. It was previously big O of n for the naive solution. And in the optimized solution, we came up with a solution which does not use any extra space. In this question, we will look at how to reduce time complexity. Okay, so the question's name is best time to buy and sell stock. So say you have an array for which the ith element is the price of a given stock on day I. So on day I, any given day, that is value 7, 1, 5. So 7 is the price of stock on day 1. I is the price of stock on day 2, and 1 is the price of stock on day 2, and so on. So these values here depict the price of stock on each day. If you were only permitted to complete at most one transaction, that is, buy one and sell one share of the stock, design an algorithm to find the maximum profit. So you are asked to complete one transaction. So in one transaction, you can buy one stock and sell it once. So this is one transaction as a whole, and you have to find the maximum profit. Okay. And also says you cannot sell a stock before you buy one. So let's look at this example. So in this example, the most optimal solution, if we were allowed to sell a stock before we buy, would be 7 minus 1, but it says we cannot sell it before we buy. So the person here buys it at 1, that is on day 2, and sells it on day 5 for the maximum price later, that is 6. Okay, so the maximum profit he makes is 5. So let's look at this, the knife solution for this. The knife solution for this is for all the combinations of I and j, where, sorry, this should be j greater than I, we check the profit. So basically for all combinations, that is 7 1 7 5 7 3 7 6 7 4 and so on, we check j minus I, that is selling price minus the cost price, and we compare them each time and we get the maximum profit likewise. And this whole solution will take a time complexity of big of n square, because we'll be needing two loops, one I going from 0 to n minus 1 and the other going other j going from I plus 1 to n minus 1. So this will take a total time complexity of big of n square and no extra space, that is a space complexity of big of 1. Okay, so what is the optimized solution for this, or a single pass solution for this? Single pass solution is that in one traversal, you want to find out what is the maximum price. So let's see. First, we take two variables, one called minimum price and the other called maximum profit. We initialized minimum price to int max, that is the maximum integer in C++, and maximum profit to 0. Why these values? Because any value less than this, less than minimum price, we want to update minimum price to that value, and any profit greater than 0, we want to update maximum profit to that value. So we have selected int max and 0 respectively for these variables. Now, if prices of I is less than minimum price, that is, so if prices of I, so like if 7 is, so let's look at that with an example. So in the first iteration, the minimum price is int max. So 7 is less than int max. So minimum price gets updated and the value of minimum price is 7. So we assume that he has bought it at 7. Okay. Now, in the second iteration, if again, if minimum price, if price of I is less than minimum price, so 1 is less than 7. So minimum price again updates to value 1. And we have assumed that he has bought it on day 2 and at a value of 1. Okay, let's move further. We see that the next value is 5. In the third iteration, prices of I is 5, but 5 is not less than 1. So minimum price remains the same, that is 1, but maximum profits gets updated to 4. Why? Because 5 minus 1, that is the profit that he can make if he sells it on day 3, is greater than the maximum profit that we have initialized here. Since 4 is greater than 0, the maximum profit gets updated to 4. In the fourth iteration again, minimum price remains 1 because 3 is not greater than 1. And maximum profit again remains 4 because 3 minus 1 is not greater than 5 minus 1. In the fifth iteration, minimum price remains 1 for the same reason again, because 6 is not less than 1. But the maximum profit now gets updated because 6 minus 1, 5 is greater than the previous profit that we were having, that is 4. In the sixth iteration, the minimum price remains same, but the maximum profit also remains same because 4 minus 1 is not greater than 6 minus 1. And so at last, the value of max profit will be the answer that we want, and we have to return maximum profit. So in the fourth step, we have returned maximum profit. So in this way, in one traversal, we have come up with the maximum profit that the person can make. Okay, let's look at the code for this. So in this code, I have initialized minimum cost as int max, maximum profit as 0. And again, if prices of I is less than minimum cost, I update minimum cost to prices of I. Else, it goes into else only if it is greater than minimum cost. So if it's greater than minimum cost, I assume that he has bought it And if he has bought it, and only if the profit he makes is greater than the profit that he had before, it updates the maximum profit. Else the maximum profit remains same. And at last you just return maximum profit. So yeah, the time complexity of big O of n and the space complexity is big O of 1. Okay, so let's move to the next question. In this question, we are going to see the greedy technique, how to solve questions using greedy technique. This is just one example. There are many out there. And not all of them are supposed to be used, solved in the same way, but then you'll get a hang of them as you practice them. Okay. So let's see what does the question have to say. Given an array ARR denoting heights of n towers and a positive integer k, you have to modify the height of each tower either by increasing or decreasing them by k only once. So the question says you are given two integers k and n, where n is the size of array, and you are given a k, and you have to do one operation on the array. So what is the array? The array is the heights of the buildings. So 1 is the height of the building or the tower, the first tower. 5 is the height of the second tower. 8 is the height of the third tower, and so on. Okay. The operation that you have to perform is either increase the height of each. So you have to increase the height of one tower or decrease its height. And for every tower, you have to perform this operation. And you don't have an option of not doing that on any tower. So for every tower, you have to perform this operation. So what do we have to find? Find out what could be the possible minimum difference of the height of shortest and longest stars after you have modified each star. So after doing the modification, you get a new set of values. What is the difference between the maximum value and the minimum value in the modified array is what the question is. And it also says after modifying the height, after modifying the height should not be a non-negative integer. That means in this question, for example, the k equals to 2. So you can't decrease the value of the first star because it goes to -1, which is not allowed. So you have to increase it. So yeah, the solution, let's see the solution for this. Let's see the solution for this problem. And the output here given is 5. The explanation for this is the height of the first star is increased by 3, and the heights of the next 3 stars is reduced by 2. Sorry, the first height of the first star is increased by 2, and the rest of the 3 it's decreased by 2, and therefore the difference between the highest, the largest star, and the smallest star is 5, and hence the answer is 5. Okay, so before going to the solution, let's see what if we are given only two buildings. What if we are given two buildings of heights respective of heights 2 and 7 maybe, and we are given a value k of value 2 again, and we are asked to reduce the heights, minimize the difference between heights by performing an operation. And the operation says I can either increase the height of each building or increase the height of a building or decrease the height of a building. So the most optimal solution that I can come up with, increase the height of small tower by 2 by value k, and decrease the value of the highest star by k. So it goes to 4, 5. And this is the most optimal solution. So yeah, so if I'm given two buildings, the most optimal solution is increase the height of the smallest star and decrease the height of the highest star. Now let's see what if there are more than two buildings. So in this case, we had more than two buildings. Increase the height of the smallest star, decrease the height of the largest star, and they have decreased the height of the remaining two as well. Why? What if I increase the value of the second tower? It goes to 7 and 7. So 3 and 8 are the small and big values after I have done for the edged buildings. If I increase this the fifth tower by 2, it's 7. It is still not affecting the range, that is 8 minus 3. So it doesn't matter. Even if I reduced 5 by 2 or if I increase 5 by 2, it doesn't matter. But what if I increase 8 by 2 and not decrease 8 by 2? In the solution, they have decreased it by 2 and hence it is 6. But what if I had increased it by 2? If I had increased it by 2, the height of the longest star would not be 8 anymore, but it would be 10, because 8 plus 2 is 10. Then the difference would be 8 minus 10 minus 3, that is 7. And that's not the minimum. We have to come up with the minimum difference. Let's look at another example for this. Okay. So this example, we'll use this example to also find the solution. So the first step is sort the array, because we want to know what is the minimum, the smallest star and the maximum star. So the first thing, I've sorted the array. So it was 3, 10, 5, 7. Now it's 3, 5, 7, 10. The edge cases are array of 0 and array of n's. That means the smallest building and the tallest, and the smallest building and the tallest building. Okay. I have to increase the height of the smallest building. So what I have done is small, I have taken a variable called small for the smallest building and I've increased it by 5. That is the value of k here. Increased it by 5. It becomes 8. And I have taken a variable big for the largest building and I've decreased it by 5. And it has become 5. Now if we observe, the value of small is 8 and the value of big is 5. That means the value of small is greater than this value of big. Hence, we swap them. So the value of small has become 5 and the value of big has become 8. Now, what about the rest of the buildings? So it was the initial heights were 3, 5, 7, 10, and the value of k given was 5. So I had taken a variable small, which was initially 3, and big, which was 10. I had incremented small by 5, decremented big by 5, and because these values now have crossed each other, I swap them, and small becomes 5 and big becomes 8. I hope this is clear. So I have performed the operation on the extreme buildings. I have to consider the middle buildings now. Let's see what if we decrease the value of 5. So if I decrease, I'll store it in a variable called sub. If I decrease the value of 5 by 5, it goes to 0. Or if I add it by 5, then it goes to 10. In both the cases, for the second building, if I decrease its height or increase its height, it is altering the range. The range initially was 8 minus 5, that is 3. But if I perform this operation on the second building, the value, either the value of big will change or the value of small will change. So we have to choose any one of these. So because we want to reduce the minimum height between big and small, that is, we want to reduce the value of big minus small, we have to choose the most optimal solution. So what if we subtracted it? So if we subtracted it, then small would be 0 and big would be 8. So the difference would be 8. And if we added it, small would still be 5, but big would be 8. Sorry, big would be 10. And the difference will be here will be 10 minus 5, that is 5. So if we reduce the height of the second tower, the difference that we are getting is 8. But if we increase the height of the second tower, the difference that we are getting is 5, because the value of big is changing, not the value of small. But so the better option is that we decrease the height, that we increase the height of the second tower, because it is giving us a less difference. And the whole point is to reduce the difference between the big and small. So we discard reducing it, and we choose increasing the size of the second tower. Okay. So what about the third tower that is of height 7? So after increasing it, the value of small becomes 5 and big updates to 10. It was previously 8. Now it updates to 10. Now for the third tower, if we increase its height, it goes to 7 plus 5, that is 12. If we decrease its height, it goes to 7 minus 5, that is 2. Okay. Now, if I increase its height, the value of big updates to 12. And the difference, if I add it, if I add it, becomes 12 minus 5, that is 7. But the difference, if I subtract it, becomes 2 minus 10, that is 8. What is the more, what is more optimal? What is the thing that we need? We need the minimum difference. So we add 5 to 7 instead of subtracting 5 from 7. So we get the difference between, so big updates to 12 and small still remains 5. And we have completed the operation on all the 4 buildings. We had first done it on 3 and 10, and then 5 and 7. So the answer we get is big minus small, that is 7. So this is the idea for this solution, this question. The solution for this question is this. So the idea is to keep the added up value or the subtracted value within the range. In this case, the added value and the subtracted value both were exceeding the range of small and big. None of them was lying inside the range of small and big. So we had to select the more optimal one. But if any one of the added up value or the subtracted value lies in the range of small and big, we'll stick to that. We won't change small and big. Okay. So, but if that is not possible, we choose the better option between add and subtract. How? We choose the one that increases the range least. So we are choosing the one that increases the range between big and small least. Okay. So we'll look at the solution for this. First, we sort the array. I have initialized 2 variables, small and big. Small is the least, the first building which has this lowest height. I increase it by k, and then we reduce the highest star by k. If small is greater than big, swap them. That's what we did here. Because 3 plus 5 was greater than 10 minus 5, we swapped them. And then for every other tower from I equals to 1 to n minus 2, we check if the added up value or the subtracted value. So add contains the value if I added k to it, sub contains the value if I subtracted k from it. If any one of it lies in the range of big and small, so if subtracted is greater than equal to small, or add is less than equal big, add is less than equal to big, I just continue. Else, if this does not happen, that means both have exceeded the values of big and small. I choose the more optimal one and return minimum of answer and big minus small. Answer has the value, the initial difference between the heights, because there can be a condition where just increasing the heights of all the buildings is the more optimal solution, because the difference would remain the same. The difference would be still the same because you have increased the heights of all the buildings. Okay, so this was the solution for this question. I hope you guys have understood this. And why are we calling this greedy? Because at every step, for every building, we are choosing the more optimal one. The more the solution that is giving us the more optimal solution, the answer that is the minimum. So in every step we are choosing a local optimal solution, hence it is called a greedy solution. Okay, so the last question that we are going to see today is about the maximum subarray sum. So I told what a subarray is before. So we'll just look at an example. So if you look at this example, the maximum subarray sum, the question says that you have to return the maximum sum of a subarray in the whole array. That is, in this example, 4 minus 1 minus 2 1 and 5, this subarray has the maximum sum 7. If you include any other element apart from these 5 elements in this subarray, the sum reduces. So you can check the maximum sum here is 7 and it will remain 7 no matter what. Okay, what is the naive solution for this? The naive solution is come up with all subarrays, which I told was a operation of time complexity n square, and check and add the elements of all the subarrays and return the one which has the maximum sum. Okay, the code for it will be for I equals to 0, I less than n, I plus plus, and for j equals to I, j less than n, j plus plus. That these two lines are for generating all the subarrays. So we get each subarray after every iteration, a new subarray after every iteration, and for every subarray, I'm calculating the sum. The innermost for loop is for calculating the sum, and if the sum is greater than max, I update max to sum, and this is how we get the maximum sum using the naive solution. This solution has a time complexity of big O of n cube. But can we reduce it to big O of n? Can we solve the same question uh, with in a single traversal, in a single array traversal or a single pass? The question is yes. The answer is yes, and we have to use Cadane's algorithm for that. So let's see what Cadane's algorithm is. So Cadane's algorithm says we have to initialize two variables, one called maximum so far and the other called maximum ending here. So maximum so far is the answer, will contain the answer that we'll be needing after the whole traversal of the array. Maximum ending here, let's analyze what this maximum ending here is. So for any, 1 second, I'll just, yeah. So for any given array, so for example, for array -2, -3, 4, -1, -2, 1, 5, and -3, the maximum sum of sub arrays ending at index 0 will be -2 itself, because there is no element before it. So any sub array ending till here, so when I equals to 0, maximum sum till here is -2. For I equals to 1, the maximum sum can be -2 plus -3 or just -3. -2 plus -3 is -5. -3 is greater than -5. So the maximum sum ending here is -3 and not -5. And at the third index, if you look at the third index, sum of all subarrays possible will be -2 plus -3 plus 4, -3 plus 4, or just 4. The maximum out of these three is just 4. So the maximum sum ending here at index 3, at index 2, sorry, will be 4 itself. Let's look at the solution ahead. So maximum ending here is always equal to maximum ending here plus array of I. If maximum so far is less than maximum ending here, we update maximum so far. So for at any element, for example, if maximum ending at 4 is less than the maximum ending at maybe 5, we will update it and we'll update maximum and the total max, the maximum ending, the maximum so far. So, and if maximum ending here is less than 0, maximum end here, we update maximum ending here to 0. Let's look at this with an example. So when I equals to 0, what is this? Okay, yeah. So when I equals to 0, maximum ending here is -2, because as we see, maximum ending here was 0, and then in the first step we added with array of I. It was, so it becomes -2. The next step says if maximum so far is less than maximum ending here. Maximum so far was 0. Okay. Maximum so far was 0 and maximum ending here is -2. It's not maximum so far is greater than maximum ending here. So maximum so far remains 0. Okay. And the third step says if maximum ending here is less than 0, maximum ending here is 0. Okay. Maximum ending here was -2, which is less than 0. So we update it to 0. In the next step, -3. Maximum ending here is 0. So again, step A, which says maximum ending here equals to maximum ending here plus array of I. So maximum ending here was updated to 0 in the last step. So it's 0 plus -3, which is -3. -3 is not greater than 0. That is, -3 is not greater than the maximum profit, the maximum sum. According to B step, it's not greater. So maximum sum remains 0. And -3 again updates to 0 because it's less than 0. For the third step, again, maximum ending here is 0 plus 4. Now 4 is greater than maximum so far. Maximum so far it was 0. 4 is greater than 0. So maximum so far updates to 0. And because 4 is greater than 0, maximum ending here remains equal to 4. Remains 4. After this, in the next step, it is -1. So maximum ending here at -1 will be 4 minus 1, because it is always maximum ending here plus array of I. Maximum ending here was 4. So it's 4 minus 1, that is 3. Maximum so far is 4 plus, so it's maximum ending here. So since maximum so far is not greater than maximum so far is greater than maximum ending here. So maximum ending here is 3 and maximum so far is 4. So maximum so far remains 4. And since 3 is not less than 0, it remains 3. Okay. In the next step, it again 3 minus 2 is 1. Maximum so far remains 4 because 1 is less than 4. And since 1 is greater than 0, it remains 1. And after that, in the next step, again, we get 1 plus 1. Maximum ending here is 2. Maximum so far remains 4. And since 2 is greater than 0, maximum ending here remains 2. In the next step, in the second last element, maximum ending here goes to 7. Now, maximum ending here is greater than maximum so far. Maximum ending here is greater than maximum so far. In the B condition, we are checking that. If this is true, then maximum so far is maximum ending here. Since 7 is greater than 4, we update maximum so far to 7. And since 7 is greater than 0, maximum so far remains 7. And in the last step, again, 7 minus 3 is 4. Maximum ending here updates to 4. But since 4 is less than 7, maximum so far remains 7. And maximum ending here remains 4. So after the whole traversal, 7, that is maximum so far, is the answer. And we return maximum so far. So in this question, we had used the maximum ending here value, that is maximum ending for all the previous values to compute the maximum so far. Hence, it is a problem of dynamic programming. We are using the values computed for the previous elements to compute the value for the present element. So yes, this was Cadane's algorithm to calculate the sum of all subarrays in time complexity, the maximum subarray in a time complex with a time complexity of big O of n. Let's look at this code for this. I have initialized max. The max here, maximum, the max is maximum, the overall maximum, and max underscore here is maximum till here, maximum here. So yes, if maximum here equals to maximum here plus array of I, if maximum here is greater than max, we update max to max here. But if it is less than 0, then we make it 0. Otherwise, if we didn't make the 0, the maximum ending at position 1 for I equals to 1 would have been minus 5 and not minus 3. So if we omitted the step C, if we omitted step C, the maximum ending at at index I equals to 1 would be minus 5 and not 3. But ideally, it should be minus 3. So that was Kadian's algorithm, and I hope you guys understood this question. And this is the code with a time complexity of big O of n. And that's it. And thank you so much.
So thank you, Sumant. It was a great session. There are some couple of questions. Let's take one by one. Okay. Uh, I guess Sumant is not there. Yeah. Okay. So it's a great session. So don't forget to attend the webinar for tomorrow, which is on bit manipulation. So thank you so much, guys, for joining us today. Hope you enjoy this session, and we will see you tomorrow. So don't forget to like, subscribe, and comment to our channel. So bye, everyone. Bye.